We're going to talk about refraction today, and refraction is the idea that the path of a light ray will be deflected or change its direction because of some change in the medium. Now you know that light rays travel through a medium, let's say something like air. But when it goes from air into something else, let's say water, and this represents the path of a light ray, let's say. We're going to measure the angle, just like always, relative to the normal. So there's some angle right there. Let's call that theta 1. That's the incident angle. When the light ray refracts, its path is changed. So this might represent the path that it would normally take, and that path would be a straight line. But when it enters the water, that's the medium where it changes. So at this interface, something happens and the path is changed, and it may be deflected like this. And we get a new angle down here, which we'll call theta 2. Okay, that's the idea of refraction, that the path changes due to some change in the medium. All right, now when we were talking about reflection, we had a law of reflection, and it was very simple. Angle of incidence equals angle of reflection, and that was it. Everything else sort of fell out of that. Well, now that we're talking about refraction, we also have a law of refraction. But the law of refraction has a common name called Snell's law. And Snell's law looks like this. In the air, you have some quality, some characteristic of the air, which is called the index of refraction. And that would be for the air, let's call that N1, because theta 1 is on the N1 side here. And then the water would have a different index of refraction, N2. Now the index of refraction itself is really a measure of how fast light can travel in that medium relative to the speed of light. The N, the index of refraction, is always going to be a number that's bigger than 1. And there is a table of indices of refraction in your textbook, and you should look it up. It turns out that N for air is real close to 1. So N for air is equal to 1.000293. So that's real close to 1. In fact, it is 1 out to 3 decimal places. So if you're doing calculations that only involve the first 3 decimal places, by the way, which all of our calculations do, then it's okay to just say that this is approximately equal to 1 and just say it's 1. Now, N for a vacuum is defined as 1. But you see there's not a big difference between air and a vacuum as far as light's concerned there. Some other index of refraction, let's say for pure crown glass. Pure crown glass is somewhere between 1.50 to 1.54. So 1.5 is close. Index of refraction for something like N for diamond is 2.419. So you can see here it's always going to be a number bigger than 1. Always going to be a number bigger than 1. So the index of refraction is actually defined this way. N is equal to, and it's a ratio, so speed of light in the vacuum compared to the speed of light in the material that the light is going to travel through. That ratio, since the speed of light, nothing can go faster than the speed of light, this is always going to be a number bigger than 1 then. Okay, so this is N is equal to C divided by V, where V is equal to the speed of the wave in the material there. Okay, that's the definition. So we have this index of refraction on either side here. Then let's get back to the original thing. What is Snell's law? Well, Snell's law is this relationship. N1 times the sine of theta 1 is equal to N2 times the sine of theta 2. So there you have it, Snell's law. right there. So if we have an interface like air and water, let's say this side is air and this side is water, then N1 is going to be 1.000293. Let's just say it's 1. And then N2 is going to be 1.33 for water. So let's say we have a ray of light that's coming along here, and we measure the initial angle, theta 1 is 30 degrees. The question then is, what is theta 2? Well, it's real easy to figure out, since N1 sine of theta 1 is equal to N2 sine of theta 2. N1 divided by N2 sine theta 1 is equal to sine of theta 2. So theta 2 is just the inverse sine of N1 over N2 times the sine of theta 1. And that's going to be the inverse sine of N1, 1 over 1.33 times the sine of 30 degrees. Plug that into your calculator. You end up with theta 2 equals 22.1 degrees. Okay, now in this case you'll see that theta 2 is smaller than theta 1. So the refraction bent the light ray closer to this normal than it would otherwise. Now, if we were going the opposite direction, if we were going from here in that direction, and we had some theta, it would bend more away, like that. So some other theta. So in that case, this would be theta 1, and this would be theta 2. Now, you don't have to stick with this theta 1, theta 2 thing, but let me give you a general rule of thumb. If you treat the incident ray as if it is the theta 1, then this will always work out nicely. It really doesn't matter until you end up with multiple layers. So let's say we've got air over here, and then we've got ice, and then we've got diamond, and then we've got glass, and then we've got more air over here. Well, in that case, you're going to have it enter here relative to that normal. It's going to refract more towards the normal. Maybe it refracts more towards the normal there. Maybe it refracts away from the normal, and then it comes out here. All right? Well, you need to work each one of those interfaces individually when you work a problem, just like we did here. And if you let the incident side, meaning the side where the light ray is striking, be the theta 1 and the other side be theta 2, then you don't get confused along the way. It also plays a role later on when we talk about other things that refraction is responsible for, things like polarization angles, Brewster's angle, total internal reflection, things like that. So this is the basic idea, Snell's law, and you realize that for this first one here, this would be theta 1, the angle here would be theta 2, but then theta 2 becomes theta 1 for the next interface, and so forth. So you can see then, if N1 is greater than N2, then that means the sine of theta 2 is greater than the sine of theta 1, which also means that theta 2 is greater than theta 1. But if N1 is less than N2, then the sine of theta 2 is going to be less than the sine of theta 1, which means that theta 2 is less than theta 1. Now, reflection and refraction go hand in hand. It's very seldom that you would have just one or the other. So let's say that we have a light ray that's coming from the bottom here. Let's say that this down here is water, like the water in a swimming pool, and up here we have air. So light has entered into the pool somehow, but anyway, at this point, we're looking at a light ray that's coming up like that. All right, now you realize that air has a lower index of refraction than water, but if we're looking at the incident ray, this would be the N1 side and this would be the N2 side. Okay, so what case do we have? N2 is going to be less than N1, so we're going to have a refraction where the theta 2 is larger than the theta 1. So if this is the case, where that's theta 1, then the refraction is going to be farther out this direction, to where this is theta 2, like that. Okay, now I want you to notice something here. If I increased this angle, the incident angle, if I increase that, if I did something like that, so now we've got a bigger theta 1 here. Well, what's going to happen is we're going to have an even bigger theta 2 as well. So now theta 2 is going to be that. But if I increased it even more, then theta 2 gets even closer to this surface. Now, you'll notice theta 1 is always going to be smaller than theta 2. Theta 2 is the big angle here. And if that's the case, there's going to come a point here where I am incident upon the interface, but this angle goes right along the surface here. And that angle right there, let's call that a critical angle, where we have now no refracted light coming out. Instead, we have reflected light coming in like that. And since that's reflected light, well, this angle right here would also be theta C. Oops, theta C. That's a C. So those two angles right there are going to be the critical angle in that case. Well, when would that happen? Well, N1 sine of theta 1 is equal to N2 sine of theta 2. But for this to happen, theta 2 is going to be 90 degrees. So that makes this sine 1, which makes the right-hand side here just N2. And this is N1 sine of, instead of calling it theta 1, that's theta C. That's the critical angle. And sine of the critical angle is N2 over N1. N1 is the incident side here. N2 is the refracted side. So this is only going to work if we're going from something with a high index of refraction to something with a lower index of refraction. And that theta C is called the critical angle. Now, any angle, any incident angle that is bigger than theta C is going to cause total internal reflection. There will be no refraction for any angle that is equal to or greater than theta C. Now, this is the basics of a lot of optical instruments. This is the basis of fiber optics, where let's say that you have a clear, perhaps moldable Pyrex or glass here. And this is like a pipe. This is a tube. This is a fiber optic. So you can shine light in on this end, and when it goes in, it would hit the side right there. But we surround this with a cladding, something called a cladding that has a higher index of refraction. Okay, so we just wrap that around the fiber optic. And this is the cladding. This is maybe some kind of glass. Well, what happens is we have total internal reflection then, and the light can bounce back and forth and go through this tube here. All of the light is passing through the tube itself, and none of it is escaping or refracting outside of the glass tube. So what you put in on this end comes out on this end at the speed of light. So if you create a light signal, you encode a signal on this end down here, and then that signal comes out on this end down here, and you have the electronics on each end to both encode and to translate that, then you can communicate effectively at the speed of light then. And that's very useful for communications, especially over very long distances. So fiber optics work on this principle of total internal reflection. Now I said that reflection and refraction occur together, and they do. So oftentimes what will happen is at an interface, you'll have an incident ray coming in, and some of that will reflect off at the same time that some of it will be refracted down in this direction. Okay, that's not necessarily a straight line there. So we have a theta 1 here. This angle over here will also be theta 1, and this angle down here will be theta 2. All right. Now don't let this confuse you. I know my drawings are not great, but that dashed line represents the straight line if it were to go straight through. Okay. So you have reflection and refraction that typically occur together. Now, if the incident light is unpolarized, and I'm going to show electric field vectors like moving in all these different directions here, that represents unpolarized light. Then here's what you discover. This refracted light is also unpolarized. Okay, so that's unpolarized light right there. But to some degree, this reflected light is polarized. Now, the degree to which the reflected light is polarized depends upon this angle right here. This angle for maximum polarization, that angle, theta 1, is called Brewster's angle. And it occurs when, let's call this theta b now, theta b. It occurs when theta b plus theta 2 is equal to 90 degrees. So when those two angles right there equal 90 degrees, there's a 90 degree here between here, then we have maximum polarization. In that case, N1 sine of theta sub b is equal to N2 times the sine of theta 2. And that's equal to N2 times the sine of theta 2, which is going to be 90 degrees minus theta b. Okay, so that's what theta 2 is. Just solve for theta 2 out of that equation and get that. But you can also see it here in the drawing. Then this is the same as N2 times the cosine of theta b. That's a trig identity there. So we have N1 sine of theta b is equal to N2 cosine of theta b. Now, if we take the sine and divide it by the cosine, then we have N2 over N1. And what is sine over cosine? Well, that's tangent. So tangent of theta b is equal to N2 over N1. This gives you an equation then for the angle for maximum polarization. When you reach theta b, then all of the reflected light is polarized. This is why, by the way, sunglasses good sunglasses are typically polarized sunglasses. They block out some of this reflected light, especially if you're fishing and you're on a lake here. Then the reflected light, the glare, when you look at the lake towards the sun, you'll see a lot of glare. But if you put on your polarized sunglasses, then the polarization filter will block out a significant portion of this light, and you can see better then. So Brewster's angle, that right there. So here's a good problem that I usually give as a take-home problem. It would be a timed problem this semester if we were doing this, but I'm not going to give it to you. I'm just going to show this to you. We'll figure it out together. Let's say that I have an interface here that has some thickness from there to there. We'll call that thickness D. And over here I have an index of refraction that's N1, and over here is N2. That makes this the incident side. So let's draw a normal to the surface here of light coming in at some angle there. And this would be theta 1. All right, now that's going to refract, and I will go ahead and tell you that this is the index of refraction for N2 is greater than N1. So this, you could think of this maybe as air and this is glass. In fact, that's a good thing to just make that assumption right there. Then the refraction is going to be more towards the normal here, so we're going to end up with something that looks like that for our theta 2 there. Okay, now if I extended that on across here, just like that, and now extend this one, create a normal here, then when it gets here, this angle here is also theta 2. And over here, this is N1, so this once again is air. Well, when this refraction occurs, it's going to be more towards the normal in this case. I'm sorry, more away from the normal in this case. In fact, it would be parallel with the original here. Something like that. That angle there, if you did some geometry here, that theta 1 is the same as that theta 1. In other words, the incident ray goes in at an angle of theta 1. It refracts on the interior of the glass, but then it also exits at theta 1 at the same angle. Let's do this. Let's say I want to find out what this deflection is. In other words, I'm going to draw a line straight through from the original. So the original would have been along this line here. If the glass had not been there, that would have been the path of travel for the incident ray. But it was deflected. And it was deflected by this amount. Let's say that we'll draw 90 from there to there. Let's call that distance x. The question is, what is x? Okay. Here's what I want to do. I want to find x in terms of the things that I know. And I know N1, I know N2, I know D, I know theta 1, and I know theta 2. We can determine those things. You can use Snell's law if you know to get theta 1 and theta 2 if you've got some of these things here. Okay, but let's say all those things are known, or you could get to them real easily. Well, what we need to do is figure out this x here. Now this becomes a geometry problem at this point. But I want you to look here and see that, first of all, this distance here, that's d. Okay? And then we have a triangle here, and this is the hypotenuse. So that's going to be the hypotenuse of our triangle. But we've got two triangles here. Here's one triangle right here with the D, the H is the hypotenuse there, but there's this distance here as well. And then we've got another triangle here that's also has H as a hypotenuse, and X is the one of the sides there. That angle there, let's call that angle phi, so we don't confuse it with the others. But that angle phi is, if I took phi and I added theta 2 to it, that angle there is theta 1. And you can see that here. Both of those together equals this angle here. All right? So what does that mean? That means phi is actually theta 1 minus theta 2. Okay, just keep that in mind. Also notice the cosine of theta 2. What's the cosine? The cosine of theta 2 is the adjacent over the hypotenuse. That's equal to d over h. So h, the hypotenuse, is equal to d over cosine of theta 2. That means I could figure out what h is because I know what d is and I know what theta 2 are. All right, then in that case, now look at this angle here, the second triangle, this lower triangle here. And the sine of phi, what is the sine? The sine is opposite over hypotenuse, so that's x over h. Now x is what we're after here. So we can solve for x. X is equal to h times the sine of phi, but h itself is d over cosine theta 2 multiplied by the sine of theta 1 minus theta 2, which is what phi is. There, we've just figured out what this is. So if we have values for n1, n2, d, theta 1, and theta 2, then we could get this. We could get this pretty straightforwardly. Okay. You'll notice it doesn't really depend upon n here. It depends upon those angles. Of course, those angles depend upon n, so they are directly related to each other. All right, but I usually give this as a homework, timed problem, whatever, take home for students to figure out and find the relationship for x. Find x in terms of these things, and we did here. Okay. Okay, now so far we have talked about light as if all wavelengths have the same index of refraction, but the problem is that's not true. That leads to something that we call dispersion. And dispersion is the idea that the index of refraction changes for wavelengths, and it works this way. Longer wavelengths of light have lower indices of refraction, and shorter wavelengths have higher indices of refraction. So which can bend more, red light or blue light? It turns out that the shorter wavelength, blue, has a higher index of refraction, so it's going to be refracted more than red light, which has a longer wavelength because it has a lower index of refraction. That leads to this idea of dispersion, and dispersion works like this. I know you've heard of a prism, which is sort of a triangle of glass, and if I take light, like white light, now white light consists of all of the various colors of light, so we're talking visible light at this specific time. So white light consists of all the red, orange, yellow, green, blue, indigo, violet, all the Roy G. Biv colors there. And when that strikes the prism, well, you have different wavelengths, which white light contains all of the visible wavelengths. The different wavelengths will refract differently. So maybe you get that one for red light because it's refracted less, and maybe this one for blue light because it's refracted more. And then when it comes out, it does something like this. So this would be red light on this end, this would be blue light on this end, and then all of the other colors in between those two would fall here. If you were to project this onto some kind of a board or a detector, you would find out that all of the Roy G. Biv colors show up there, all the colors of the rainbow. So that's how you create a spectrum. It's because the index of refraction is different for each of the various wavelengths. Now, this is an important aspect in science because the science of spectroscopy shows up in a lot of areas of science. Geology, chemistry, astronomy, physics, all depend upon being able to take light, break it up into its component colors, because if you break it up and you spread these out far enough, you can see individual lines, emission and absorption lines, inside the spectrum. This is also what's responsible for things like rainbows. It's also responsible for chromatic aberration. Chromatic aberration just means that the colors are focused at different places. For example, let's say that we have a lens. This is a glass lens. It's got a curvature on each side. Well, I don't know if you've thought about this, but if you look at it from the side here, that's a prism right there. So if you have a lens that has edges to it like this, then you're going to get dispersion in the corners here at the edges. So what does that mean? That means that, a whole purpose of, let's say if this is an eyeglass that you wear glasses, the whole point is to bring light to a focus, to a point, so that you can see better. It corrects your vision. But if you have things like, one color focusing back here and another color focusing up here, well, then you end up with blurred image back here. So I've kind of given it away here. Refraction is what allows lenses then to focus light. So we're going to spend probably the rest of our time here talking about lenses. Specifically, we're going to talk about thin lenses. Now, thin lenses have a focal point, just like mirrors did. They also have a focal length, just like mirrors did. The difference is that our lenses could have two sides. So if we have, let's draw an axis here, let's put a lens here on the axis. You see there's two curvatures here. We've got a curvature on the front surface, a curvature on the second surface. So we're not going to worry too much about these curvatures, because we're going to assume that we have thin lenses. It is possible to have one curvature on one side and a completely different curvature on the other side, but we're going to assume very simple cases, thin lenses, very little curvature. We don't have to worry about chromatic aberration, especially if we stay close to the axis here and we don't get too close to the edges, then it won't be a problem. Now, you can also have two different kinds of lenses. What I've drawn here is considered a converging lens. Converging lenses do exactly what it says. They converge light. So light comes in one side and it converges on the other side. That's the whole idea of a converging lens. Magnifying glass would be an example of a converging lens. But you can also have another type of lens called a diverging lens. And that might look like this, where the curvature is the opposite of this. We're looking at both of these from the side. Now, a diverging lens, the rays of light that come in on one side don't converge to a focus. Instead, they diverge. So this is a diverging lens, that's converging lens, and you can tell the differences here. All right, now we can use ray tracing to find to go from object to image for all of these, and they follow the same rules, sort of. For example, let's say that we put an object over here. Well, now you have a focal point that's on either side of the lens. So you've got a focal point there, but you also have a focal point back here. Remember, we're going to assume that those are the same distance away, because we're going to assume curvature is being the same on both sides of the lens. So we have two focal points now. All right, so the rule that says if a light ray comes from an object that is parallel to the axis, what happens to it? I'm going to draw a line right through the middle here, and we're going to assume that that represents the interface where the refraction happens. Well, it's going to refract. If a light ray is coming in parallel, it's going to refract through a focal point. So how does that work? It goes right through the focal point just like that. Okay, well, what about if it goes through a focal point? Well, you see, here's a focal point here. If it goes through a focal point like that, then when it refracts, it comes out parallel like that. So your image would be located right here if we did ray tracing. All right, now this is the center of the lens right there. So if light passes through the center, it goes straight through the center, just like that. So it passes through that focal point, not that focal point, but that point as well, where the light rays are focused, and this creates the image there. So all three of those will create an image, and they should converge, and they would, of course, if I drew it carefully with straight edge and made all my measurements real carefully. Now for a diverging lens, they also have two focal points on either side of the lens. So if I have a object over here and I have a ray of light that's coming in parallel, well, there's the plane where the refraction is going to occur. What happens? Well, a parallel, it refracts away, it diverges. So it's not going to converge, it's going to diverge. Well, where does it diverge? It diverges as if that ray of light came from this focal point, and it's this focal point on this side. Now, this is still the center of the lens here, so a light ray would go through the center like that, uninterrupted. All right, but what about the third one? Well, if you have a ray that's heading towards a focal point, now which focal point? It's this one over here. So if you have a ray that's heading towards a focal point over here, now it didn't get to that, but it was heading towards it. Now when it refracts off parallel. There. So you can see these rays diverge. There's no place where they converge. So how does it form an image? Well, you trace back all of these. And what you would discover is